So we're going to go from 0 to 5, and here we go. All right, and that's fine. So what I do here is I go to second table, right? And I'm going to put in, let's say, you always want to put in the endpoints, right? So 0, yeah. So 0, it's 2.9. So here, 2. So these are going up by 4s, right? By 0.4. So if this is 2.4, that's 2.8. So 2.9 is a little bit above that, right? And then let's say at 4, it's 3.4 here, right? And let's say at 12, it's 3.879 here. And then at 16, 3.947. And how much is it at 20? A little bit higher, right? So it just keeps going progressively up like that. Okay? All right. So use the graph to estimate the number of bacteria present after 8 hours. Once I have my calculator, I could just put in 8. And it says 3.736, so 3.7 grams. Now, one thing that is super important that I did not do on this is I did not label my axes, which I'm going to do right now. So what is the horizontal axis going to represent in this case? Time. And I say time, unit is what? Hours. Super important. And what about the vertical axis, the dependent variable? Weight in grams. Okay, now this is a meaningful graph. Fabulous? Fabulous. Okay. Find the limit as t approaches infinity of f of t. According to the graph, what do you think the limit is as t approaches infinity? According to graph, limit as t approaches infinity of f of t is equal to 4. Let's justify algebraically, because why not? Brandon, if you're having trouble seeing, do you want to move here? You okay? Okay. Let's justify algebraically. All right, so this is going to be the limit as t approaches infinity of my function 4 over 1 plus 0.35 e to the negative 0.2t, right? So what is that? What's e to the negative 0.2t? Let's write it in a format that is more accessible, let's say. Okay, so it's going to be 1 plus 0.35, and this is 1 over e to the 0.2t. Is that right? Right? Okay, so as t approaches infinity, right, it's e to the 0.2 of a really infinitely large number. So it's e to the infinitely large number still, right? Because even 0.2 of infinitely large numbers is infinitely large, okay? So I have 1 over e to the infinity, which is 0. So it's 1 plus 0, right? Which means it's 4 over 1. So that's 4. Isn't that cool? Right? It's super cool. Super, super cool. All right. Here's the formula, which we've seen again and again. This is the relativity formula. Basically, you have the mass m of an object traveling at velocity v is given by this cute little formula. This is like my favorite formula. M naught over that mess, right? M naught is the rest mass. So basically, if you had this, right? You weigh it. It weighs a finite amount, and but if this was traveling at a speed close to the speed of light, then it will have a different mass, Okay, so this is the mass here on Earth when I weigh it when it's standing still. Okay? So, what is the mass of the object? What is the limit of m as v approaches c from the negative side? As v approaches c from the negative side, so it's like just under c, right? So what would that be? So for example, if c is 1, then, right, then v is 0.9999, which, what would that be? Or if it's like, right, or if it's like, if c is, let's say, 5, then this would be 4.999999. It's pretty much 1. So 1 minus 1 is approaching 0. So m naught over that is infinitely large. So the limit as v approaches c from the negative side is of m naught 1 minus v squared over c squared. Right? So this, here's how we do it. This, we say, will approach 0. Okay, it doesn't equal 0. It approaches 0. I'm sorry, it approaches 1. And so 1 minus something close to 1 is almost 0. And m naught over almost 0 will be infinity. It's infinity. It's undefined. It is a solution. It's infinitely large, right? Right. It's correct because it's a limit. It's not no solution. It's infinity. So we say, for example, the mass will be infinitely large as v approaches c. Okay? Yes or no? I mean, it doesn't matter. And this is where you get E equals mc squared, because if something even tiny is traveling at nearly the speed of light, then it'll have like infinite amount of energy, right? Yeah. Okay, so what we were saying is V is approaching C. Okay, so C in actuality is 3.3 times 10 to the power of 8 meters per second. Okay, whatever. Suppose C is a more like feasible number, like 5. Okay, and if V is approaching C from the minus side, so if C is 5, then V would be like 4.99999, right? So if you have 4.99999 over 5, that's relative, like it's very close to 1, right? It's like 0.00000, it's like 0.9999999999999. 1 minus that, 1 minus practically another 1 is almost 0, right? So the denominator will be approaching 0, and anything divided by that tiny amount is infinity. Yeah. Just the opposite. Right. Okay, let's talk about that, yeah, later. Okay, Matt determined that the voltage in an electrical outlet in his home is modeled by this equation. Explain the significance of this. So explain the significance of this. What does that represent? Okay, limit V of t as t approaches infinity. What does that represent in real life? Like, what is that? If you were to explain that notation to somebody who doesn't know any math, what would you say? What is that? Not velocity. This is not talking about voltage. It's the voltage where time. Right? Right. So this represents, right, the voltage in the electrical outlet after a long period of time. It represents the voltage in electrical outlet after a long period of time. Okay, now it says, does it exist? Does it exist? Right. So the limit as t approaches infinity of 140 sine 120 pi t. Okay? Okay, what type of function is this? It's a sine function, yes? Yes? Okay. It's a sinusoidal function. What's the amplitude? 140. And then, so, you know, it's oscillating, right? So, what is the limit as t approaches infinity? Right, it does not exist, okay? In fact, v of t will oscillate between what and what? Positive, not positive and negative? Positive and negative 140. Positive 140 and negative 140. So I don't know. It could be 139. It could be 0. It could be negative 2. Okay? Okay. A pool can, okay, so those were from 12.1. I did separate them into sections. So here are some from 12.2. A pool contains 75,000 liters of pure water. I actually like this problem. So 75,000 liters of pure water. They just filled up this water. Okay? Brand new. A mixture that contains 0.3 grams of chlorine per liter of water is pumped into the pool at a rate of 75 liters per minute, right? So you're not like dumping a bucket of it. It's continuously being pumped into the pool, right? And the solution is 0.3 grams per liter, okay? The concentration of chlorine in grams per liter, all right? So the concentration of chlorine in grams per liter t minutes later in the pool is given by this. So let's think about that. In the beginning, how much chlorine is there in the water? 0. And then as you start pumping it in, you're adding in little by little by little by little. So it's increasing, right? Okay, so it says to find the limit of this, right? So you know what? It asks to find the limit of the concentration as t approaches infinity. But you know what? I'm going to go further than that. First, let's find the limit as t approaches 0 of c of t. So this is the limit as t approaches 0 of that function, 0.3t, 1,000 plus t. What does this physically represent? What does this physically represent? The concentration at the very beginning, before you start pumping. This is the concentration at the very beginning. How much is it? 0. Does that make sense to you? Yes, that makes sense to me. So now let's go and ask what the problem was actually asking us. Let's go and find that. That's the limit as t approaches infinity, 0.3t over 1,000 plus t. Now, if we're looking at an infinite limit, what do? You know, you don't want to tell me. You take what? You take the ratio of what? Of the term of the terms with the highest degree. Cool. So this and this, and yes, it'll be the ratio of the coefficients. So it'll be 0.3 over 1, right? So it's going to be 0.3. Okay. What does all that mean? What's going to be the unit? This is the limit of C of t. What are the units here? Okay, so it's going to be 0.3. So, sorry, 0.3. What is it? Grams per liter. Whoops. No, it's grams per liter, right? This is the concentration, so it's the grams per liter. Okay, now take a look at this question. Now it says interpret your results. So tell me what this means. Yes, tell me. Right, so not that all the, so it's being continuous. You're never going to run out of chlorine, right? But after an infinite amount of time, after a very long period of time, the concentration of the pool is going to be 0.3. And what is that a significant number? Is that a significant number? Did we see it before in the problem? It's the same concentration of what you're pumping in, right? So you're pumping it in, so after a long period of time, the entire pool will have the same concentration as the solution you're pumping in, right? And that happens because you're not putting in a fixed amount, like you're continuously pumping in new and new and new. But the other side of it is that it will never surpass that concentration. So you could keep pumping it in, but you're never going to have more. Okay? So, as t approaches infinity, the water in the pool will have a maximum concentration of 0.3 grams per liter, which is the same as the mixture being pumped in.
Wait, is the mixture pumped in?
Okay, still do. Okay. Flint, not the city, bought a new motorcycle for $24,000. Okay? Suppose the value V of his motorcycle in thousands of dollars after 2 years can be represented by this equation. Okay. Say that again. Thank you. That was going to be the question I was going to ask first. Is this gaining value or a losing value? It's losing value. How do we know that? Right, but how do we know it off the equation? The rate is less than 1. Fabulous. Complete the table around answers to the nearest hundredth. I'm not going to insult your intelligence too much with that. So basically, for t equals 1, we plug in a 1, and we get 23.52. So is that how much it costs? $23? Right? 21.69. 10 years after, it's 19.61. Sure enough, it's losing value, right? Huh? Well, it said here that the value is in thousands of dollars. That's how it's defined, so we could just use smaller numbers. Okay? All right. Okay, so let's find the limit as t approaches infinity of v of t. Well, make up your mind. Oops, what did I do? Of t, it's even in the screencast, right? So, 0.98, this is a decimal, less than 1, to a higher power. It's going to get, less and less and less towards 0, and something that's almost 0 times the number is still almost 0, so that's going to be 0. Okay, so after a long time, the motorcycle is, well, let's not say it's worth nothing. Let's say it will have 0 value, right? Okay. All right. Right, right, so it has a $0 value, right? Okay. the cost C of producing a certain, okay, so here's what we're going to do for this one. You're going to do this one on your own, A, B, and C, and you're going to stop after C. So A, B, and C on your own, go. I think most of you have had an opportunity to do this. Let's just go and give the answers. So here, the cost of producing 100 parts, we would say C of 100, that's the proper notation. And we would say how much? $5,000, right? Right? And here, how many parts did the company produce for 900 parts? Oh boy. And here, what is the average cost? $20.20. Huh? I can't do that one. So this will be the limit as P approaches 15,000 of C of P, which was what? 3,000 plus 20P over P, right? So what is this, by the way? This is the average cost per part, right? As what does P stand for? Parts. So, you know, as you produce 15,000 parts, if you're producing 15,000 parts, then the average per part is what? So this will just be, you just plug in 15,000. So it'll be 3,000 plus 20 times 15,000 over 15,000. And no, that's 150. You should get $20.20. Yeah? Okay. All right. I will stop here for today. I'm going to hand out the